Before we jump into the 9.3 notes, I want to remind everyone of the 3 tests for convergence / divergence that we have already learned, because we have a list of 10 that we're building up to, and it's worth reviewing just to remember that this list is all the elements on the list are important. So, for example, the first one is telescoping series. And that is when we've got lots of positives and negatives that end up canceling each other out, and we're left with a finite number of terms. Partial fraction decomposition is often used with telescoping series. We've got the geometric series test, which is great because that tells us not only if it converges or diverges, but also what the value of convergence is, right? This is the sum when n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that the absolute value of r is less than 1. Okay, that's an important one. And then we've got the nth term test for divergence. The nth term test only tests for divergence. And that says that if we find the limit as n approaches infinity of the individual terms that we're adding, right, the values that we're adding up, if this does not equal 0, then our series diverges. Super important to remember that the converse is not true. If the limit does equal 0, it means nothing. All right, so 2 more tests to add on to this time. We're going to have the integral test and the p-series test. The p-series test is an extension of the integral test, so we'll start with the integral test. First off, we want to talk about the integral test by comparing it to a continuous function. We're going to say that if the sequence is equal to a function, remember that the only difference between these guys is that x is a continuous function, whereas x is a continuous variable, where n is a discrete variable that we only allow to be finite values, like or discrete values of integers, positive integers normally. But we can compare these, and if it's true that this related continuous function is positive, continuous, and decreasing for all x values greater than or equal to 1, then we can say that the infinite series and the improper integral, both going from 1 to infinity, behave the same way. Either they both converge or they both diverge. All right? Now this should make a little bit of sense if you think about it. If we have a positive continuous decreasing function like this over here, and I'm asking the question, how does this compare to the sequence where a sub 1, this is 1 comma a sub 1, and this is 2 comma a sub 2, etc. If we take a look at the sum from n equals 1 to infinity of a sub n, well, I'm just adding up a sub 1 plus a sub 2 plus a sub 3 plus etc. And graphically speaking, geometrically speaking, we can think about this as being the area of a rectangle whose height is a sub 1 and whose width is 1. So the area of this rectangle represents the first term in our series, and the area of this rectangle represents the second term in our series, and then the area of this rectangle represents the area of our third term. So the area is a sub 1, the area of this is a sub 2, the area of this is a sub 3, etc. All right? Now this should look an awful lot like Riemann sums, because it is right Riemann sums, a rectangular area method, a right rectangular area method. And if we ask the question, can we find the exact value of the shaded region that goes forever off to the right, that's going to be something that we've dealt with already back in chapter 8, right? We can say that the integral from 1 to infinity of f of x dx is definitely related to the sum of these areas of these rectangles, in that this sum is a little bit bigger, but a good approximation of this. So if this shaded region diverges to infinity, then the series, which is bigger, it's an overestimate of the area, must diverge as well, because it's bigger than infinity. So it's another infinity, must diverge as well. All right, we can perform a similar but slightly more complicated discussion if we want to talk about convergence, right? We could change this word to converges if we change this to converge as well. But it's not going to be quite as immediately obvious because in this case, the bigger one is going to be the one that we're interested in. So if we know that the smaller one converges, that does not mean that the bigger one has to converge. But we can get around that by doing an LRAM instead, and then realizing that some finite value plus one extra term is still going to be finite. So that's kind of the background behind this. Okay, so again, we have to have a function that matches the sequence that is positive, continuous, and decreasing. And those three things are requirements. And in fact, if you're going to use the integral tests, you're going to have to actually write out f of x is positive, continuous, and decreasing. You have to actually write that out each time you use the integral test. That's like the L'Hopital's rule. We have to write out the limit of the top and the limit of the bottom. You have to make sure that it is allowed that we can use that test before we actually use it. All right. Couple notes here. If we get a converging integral, that doesn't mean we found the value to which the series converges, right? If this shaded region equals a value, that doesn't mean that it's equal to this. In fact, they're not going to be equal because the rectangular area method is an approximation. So it's not that they're the same, but they are close to the same. They're either both finite or they're both infinite. Okay? The other thing you want to remember is that it's possible to have a graph that isn't always positive, continuous, and decreasing. We could have a graph that maybe starts off increasing and does a little bump like this and then turns around eventually and starts decreasing. Okay, so it's increasing for a while, but eventually for some k value that x passes, like perhaps right here, this might be k, from k on, whether that's 1 or some other finite value, if our function is positive, continuous, and decreasing, then we can still use the integral test, because what happens in finite land is irrelevant, because any finite value is not going to change another finite value to infinite, and it's not going to change an infinite value to a finite value. So just keep those 2 points in mind.